Hey there, chemists. In this lesson, we're going to look at the reasons why certain processes happen from a chemistry perspective. This is the discussion of spontaneity, and we'll see that it's controlled by some things we've talked about in the past, and then one thing we're going to introduce today. For example, just thinking about what happens when salts dissolve in water. If we were to look at our solubility rules, we should remember that sodium chloride and calcium chloride both dissolve in water. But if you measure the temperature of a solution that's made after the dissolving happens, you'll find that sodium chloride gets colder and calcium chloride gets warmer. So we know from our past discussions that means that sodium chloride is an endothermic dissolving, but calcium chloride is an exothermic dissolving. So they both have a measurable change in enthalpy, and they're the opposite of each other, but they both still happen. And the question is why? Why do these both happen if one is endo and one is exo? And exothermic processes are typically thought of as more favorable. Well, that's what the discussion from today is. So this is tied in with a couple of things we've talked about in the past. Kinetics is, remember, how fast something happens, as opposed to equilibrium, which is answering the question, which direction? And we're going to talk about both of these as we move into thermodynamics, which is simply the question, will it go? As in, ever. Are we ever going to see a chemical process happen? Not necessarily quickly, but will it occur at all? And a process or reaction that does go is considered spontaneous. That word might make you think it happens quickly, but we actually use it to just mean it eventually occurs on its own in a certain direction, not in reverse. And we'll see it has to do with three different state functions. Number one, the change in enthalpy, something we've talked about in the past. Number two, the change in entropy, which is what we're going to introduce today. And frankly, the combination of these, known as delta G, which is the change in free energy. And the first thing to note is that everything we learned in the past about changes in enthalpy is still true. We learned how to use Q equals mc delta T to perform calorimetry measurements. We could use reference pieces of information, such as these heats of formation, which exist in a table toward the back of your workbook or in any chemistry reference book. Way in the back, there's a table that shows the delta H, the heats of formation for various substances. And you'll also notice we have changes in free energy and absolute entropies of formation as well. So those are just things we can look up. There is looking at chemical bonds. There's using bond energies or bond enthalpies. And recall, if we want to look at the change in enthalpy of a reaction using bond energies, it's simply the broken minus the formed. And we did a lot of calculations like this back in the first semester. Here's the reaction you saw on the first day of the year and many times since, which is the combustion of nitrocellulose, really the decomposition of nitrocellulose or flash paper, which happens to give off a whole lot of gaseous species. If you want to go back and balance this for fun, you can. This is essentially like a combustion reaction, and you can see all the energy that's released from this when it occurs, just like any piece of paper burning. So a reminder, all combustions are exothermic. You can't tell by looking at a reaction what its change in enthalpy is, except for combustion. I'm just going to make a note. All combustions exothermic in the net. So that's just a reminder of everything that you should already be familiar with in terms of changes in enthalpy, and we'll see that these apply to some of the state functions in this unit as well. Now, entropy is the new thing for today. When does entropy change? And I'm going to talk specifically about when entropy increases. Entropy is a measure of disorder in a process, and qualitatively, this typically happens anytime we have a gas expansion It's usually when there's an increase in volume and a decrease in pressure. These are physical changes. If you have a temperature increase, solutions forming cause an increase in entropy. In other words, solid becoming aqueous. And then any phase change that's endothermic is entropically favorable. Endothermic phase changes. There's a couple of pictures on your notes that show these. Here's a gas just mixing together, in a closed system, and then combined, it's more randomized, so the entropy is increased. As we go from a solid to a liquid and a liquid to a gas, you get greater and greater entropy as a result. And just when we make more gas particles, the one here shows a chemical reaction. So these are all physical changes. Now let's talk about chemical changes. Chemical changes that you can identify as being more entropic are almost every decomposition reaction. Decomposition reactions. In other words, one thing becoming many things. For example, potassium chlorate to KClO3s will decompose to make the chloride salt, potassium chloride, and oxygen gas. So one thing becoming many things is an entropic driving force. This one I can use as an example for both types of reasons we explain chemical changes. Not only is it for decomposition reactions, but any reaction that forms more gases is entropically favored. So any reaction which produces more moles of gas. Gases have a higher positional entropy than liquids and solids. So we can just look at the gas particles that it produced and predict the entropy change. That's qualitative. What about quantitative? How do we get quantitative information about entropy? Well, there's two things to consider. There's the entropy change of the system, which for us is usually a chemical reaction, and then what it does to the surroundings. And unlike other types of energy, these are not conserved. Based on the second law of thermodynamics, the sum of the system and the surroundings is always increasing. This is the second law of thermodynamics for any spontaneous process. The entropy of what we're going to call the universe is always increasing. And the word spontaneous you sometimes might see written as thermodynamically favorable. So I'll write that as well. That's a new terminology that the AP seems to be using more these days, but the same thing, things that actually happen under their own power. So as an example, let's look at a reaction. Let's look at the combustion of methane and talk about the change in entropy of the system, the reaction itself, and what it does to the surroundings. First, let's just write the combustion reaction. That's 1 methane, gaseous, will react with 2 oxygens, gaseous, making 1 carbon dioxide, gaseous, and 2 water molecules. And even though under the temperature of a combustion reaction, it's typically gaseous water, let's say we study it when it condenses back into the liquid phase. So in order to get the entropy change of the surroundings, we need to find the delta H of the system of the reaction itself. And for that, we can go to our tables of heats of formations, which we have here in the back of your workbook. So the delta H of this reaction, the delta H of the system under standard conditions, would be the heat of formation of carbon dioxide plus 2 times the value of liquid water minus 1 times the value of methane minus 2 times the value of oxygen. But remember, elements in their standard state have an enthalpy value of 0, so we don't even need to worry about that. So the value of carbon dioxide, if you look it up, is negative 393.5. These are all kilojoules per mole, plus 2 times the value of liquid water, which is negative 285.8, minus the value of a gaseous methane, which is negative 74.6, and that comes out to be negative 890.5 kilojoules per mole of reaction. So plugging into this new equation from today, the change in entropy of the surroundings is the negative of that, negative 890.5 kilojoules per mole, divided by, let's look at it at 25C, which is 298 Kelvin, and you get a positive value of just under 3 kilojoules per Kelvin, and that's for one of those reactions. I'll put the kilojoules per mole of reaction. That's pretty small. I'll turn it into just joules and call it 2990 joules per Kelvin mole. What about the entropy change of the system? Well, that means we need a little more information, and we're going to go to the same table in the back of our book and use a different column, which is the absolute entropies of each of these substances. And all of them have an entropy. Even the gaseous element oxygen has a value for its entropy. So the CO2 is 213.8. These are in joule per Kelvin, plus 2 times liquid water, which is 70, minus the methane, which is 186.3, minus 2 times the value of oxygen, which is 205.2. And that gives us a negative 242.9 joule per Kelvin per mole of reaction. And just as a self-check, we could look at the reaction and say, we go from 1 plus 2, we go from 3 moles of gas to only 1 mole of gas. It makes sense that this reaction is actually not entropically driven, but it is enthalpically driven. There's a favorability in the enthalpy and an unfavorability in the entropy. And the real takeaway here is that the sum of those two entropies, when you add them, you can see the total is a positive value. The delta S of the universe is greater than 0, as the second law of thermodynamics dictates. So that's how we handle quantitative entropy using tabulated information, qualitatively for physical changes and chemical changes, and just a review of some things that we're going to see later in this unit that have to do with what we learned about with thermochemistry.